If you've ever watched a modern train speed past, you may have noticed something unusual above the tracks: long overhead wires stretching for miles, supported by steel poles. In other places, you might have spotted an extra rail running alongside the tracks instead. These aren't random pieces of infrastructure. They're part of an electrification system that powers many of the world's trains. Unlike diesel locomotives that carry their own fuel, electric trains receive energy directly from an external power source while they're moving. This raises an interesting question. Why are train tracks electrified? In this video, we'll explore how railway electrification works, why it's used, and why many countries continue investing billions to expand electrified rail networks. Right here on History of Simple Things. One of the biggest advantages of electrified railways is that trains no longer need to carry their own fuel. Instead, electricity is supplied continuously through overhead catenary wires, or in some urban systems like subways, through a third rail mounted alongside the tracks. The train collects this electricity using a pantograph, a spring-loaded arm that presses against the overhead wire, or a contact shoe that slides along the third rail. That electricity then powers electric traction motors connected to the wheels. Since the energy source remains outside the train, valuable space and weight that would otherwise be occupied by large diesel engines, fuel tanks, and exhaust systems can be used more efficiently. The electrical supply itself comes from power stations and is delivered through substations that convert grid electricity into the voltage and current required by the railway. Because the train receives power continuously, it can operate for long distances without stopping to refuel, making electrified systems especially practical for busy rail corridors. Electric trains are widely known for their impressive performance. Unlike diesel engines, electric motors produce maximum torque almost instantly, allowing trains to accelerate much faster from a standstill. This is particularly valuable for commuter trains that stop frequently, helping them stay on schedule while reducing travel times. Electric traction motors are also highly efficient, converting a much larger percentage of electrical energy into movement than diesel engines convert fuel into mechanical power. Another major advantage is regenerative braking. Instead of wasting braking energy as heat, many electric trains can reverse the function of their motors during braking, converting the train's kinetic energy back into electricity. Depending on the railway's design, this recovered energy can either power nearby trains or be returned to the electrical grid, reducing overall energy consumption. Combined with fewer moving mechanical parts and no complex transmission systems, electric trains generally require less maintenance and experience fewer breakdowns, making them highly reliable for high-frequency passenger services. Electrified railways provide major environmental benefits. Electric trains produce no direct exhaust emissions, improving air quality in cities, stations, and tunnels where diesel fumes can build up. However, their overall impact depends on how electricity is generated. When supplied by renewable sources such as wind, solar, hydro, or nuclear power, rail transport can achieve very low carbon emissions. Even where fossil fuels still contribute to the grid, centralized power plants are typically more efficient and better controlled than individual diesel engines. Although electrification requires high upfront costs for infrastructure like overhead wires, substations, and support systems, it often reduces long-term operating expenses. Electricity prices are generally more stable than diesel fuel costs, and electric trains use energy more efficiently. Lower maintenance needs also improve cost-effectiveness, especially on busy rail corridors with frequent services, making them economically advantageous over time for high-demand passenger and freight routes across many countries' worldwide adoption. Despite its many advantages, railway electrification is not practical everywhere. Installing overhead wires, substations, and related infrastructure over long distances requires major investment, which is hard to justify on lightly used routes. In remote areas with only a few trains per day, diesel locomotives are often cheaper because they need no extra infrastructure beyond the tracks. Electrification can also be technically difficult, as bridges may need raising, tunnels widened, and clearances adjusted to fit overhead wires. Mountainous terrain and severe weather further increase construction and maintenance costs. Freight railways add another challenge. Although busy corridors are often electrified, some long-distance routes still rely on diesel because they cross regions with different electrical systems or non-electrified gaps. For these reasons, countries usually focus on electrifying the busiest passenger and freight lines first, where long-term efficiency and environmental benefits outweigh the high upfront costs. As countries reduce greenhouse gas emissions and improve transport efficiency, railway electrification is expanding worldwide. High-speed rail relies on electricity because electric motors can sustain speeds above 300 kilometers per hour. Urban metros, commuter lines, and intercity networks are steadily replacing diesel trains with electric systems. Where full electrification is not practical, engineers are developing battery electric trains that recharge on electrified sections and continue on non-electrified tracks. Hydrogen trains are also being tested for regional use, though they face challenges in efficiency, infrastructure, and fuel production. Despite these alternatives, conventional electrification remains the most efficient option for busy rail corridors and helps decarbonize rail transport. Electrified train tracks are engineered systems that deliver continuous power to moving trains. Without carrying fuel, electric trains accelerate faster, use energy more efficiently, require less maintenance, and produce fewer emissions than diesel locomotives. Though expensive to install, they are highly effective on busy routes and support sustainable, efficient transportation. Thank you for watching. If you have suggestions for our next video, feel free to share them in the comments below. We'll be sure to give you an acknowledgement for your contribution. Thank you for joining us on this journey through the history of simple things. Don't forget to like, subscribe, and stay tuned for more stories woven through the smallest details.